And good morning, everyone. I am Hadi Zaatiti. I am a research scientist at NYU Abu Dhabi. And I'll present you in this talk our work called Towards Stable AI System for Evaluating Arabic Pronunciation. This work is a joint work with Dr. Hatem Hajri, Dr. Osama Abdullah, and Professor Nader Masmoudi from NYU Abu Dhabi. So we start with what is the problem that we're trying to address in this work, and mainly it's the recognition of letter level of Arabic pronunciation. So how can we build a system that can recognize a pronunciation of a letter? And this is a phoneme level task. And the ultimate goal is, in case we recognize a wrong pronunciation, how can we identify what is the mistake that has been done, and then how can we correct for that mistake? And the motivation comes from different things, but we mainly the current state of the art models such as Whisper and WAF2Vec2, they perform really well on tasks where we have long prompts, long inputs, such as transcription tasks, word recognition. But from what we've seen, it showed some poor performances when used for phoneme letters or very short duration of an audio input of a sample. And they performed not so good at letter level recognition in Arabic. And what is the difficulty in that problem? So what we noticed is that mainly the utterance duration of a data sample is typically very, very short. It is around, from a data set we acquired, we measured it on an average at around 450 milliseconds with some deviation of 40 milliseconds. So a classifier would require a large amount of data in order for them to really have any helpful data to train on, basically. The second difficulty is that when we're pronouncing a phoneme or a letter, there's a lack of context. So what we mean by context is basically we're trying to predict the token, basically, and then what is the set of the tokens before and after that provide this context. So when we're trying to do that with a very short utterance of a letter, this context is not there, and usually it provides a lot of helpful information for the classifier to any kind of model, transformer models, and so on, this context is very important for them to reach those performances. And in this application, this context is not there, so the classifier cannot rely on such a context. And why is this problem interesting, and what's the motivation behind? What kind of applications can we see in such a problem? So in many different domains, it is critical to have good ESR systems that are capable of recognizing letter level pronunciation accurately and assess the phonetic quality of the pronunciation. For example, speech therapy, people who, mainly young people who have problems with speech and speaking, require such tools, whether by the therapist or themselves as a user, to assess their pronunciation and give feedback and correct that. And this is very an important problem. And also the foundation models for word and sentence level models that are very good at transcription and so on, they might benefit actually from having a higher accuracy at the phoneme and letter level. And this is maybe they are already reaching high performances of 90%, but maybe this is what's needed to make them even better at being expert as like a native correction of the pronunciation, because this is when we are at the phoneme level and the letter level. Now, what is specific for the Arabic language is that in Arabic, we have some consonant letters that are emphatic that doesn't have analogs in other languages. And so the Arabic language cannot benefit from large corpora on other languages, especially for those letters that doesn't have analogs. So it makes it an interesting problem. Additionally, one very good application is basically Quranic tajweed rules, where the pronunciation of each letter separately from what's before it and after it is basically very important to assess that it is a correct pronunciation of the word. So the word must be pronounced correctly based on each letter separately, rather than the word as a whole, as in other applications. So we hope that this work supports closing some of this gap, or at least shed the light on what's this problem. So the outline of the contribution basically is the first acquisition of a high quality data set of diacritized isolated letter level of Arabic pronunciation. So we have 28 letters in Arabic with 4 different diacritics. So we're considering a 112 number of classes. Basically, we acquire such a data set. We'll show you what we did for this acquisition. We built a pipeline to train a very basic classical neural network and studied its performances trained on this data set. We also fine-tuned WAF2Vec2 and under this data set and compared performances to the WAF2Vec2 model. So additionally, we analyzed the robustness of the classifier, and then we adversarially trained it so that it becomes more robust. And then we performed an accuracy drop test under different perturbations. And that's very important in ASR, such that if there's a small noise, it doesn't completely make the classifier misclassify a sample. And that's why we did this robustness analysis as well. So the data set and the pipeline are available upon request if anybody would like to contribute. So let's start with the data collection and pre-processing part. So in order to make the data collection accessible to people worldwide from different continents and have not just from a specific country or area, we designed a mobile app and a web app that are publicly available to facilitate the collection of diacritized Arabic letters pronunciation. We also collect metadata such as age, gender, the nativeness of the person, and the continent of the collection. So please feel free for Arabic speakers to contribute to this data set, and we'll be promoting this application further and further to acquire more data. So how does the collection goes? Basically, we have the person picks the class, and then there's a model that they have to listen to and to mimic that. So there's a model that is a correct pronunciation of the of this letter, and then the person listens first to the model, and after that they can record their voice using their mobile phone or their computer, and then once they record it, they can listen again to what they recorded as a sanity check, and if they're happy with what they're listening to their voice, they can choose to submit their sample, or they can discard it and record again, and so on. So we collected around 10,000 utterances across the 112 classes, and we built a pipeline for pre-processing. So one of the first steps is basically, many times we have some silences at the beginning and at the end of the pronunciation. So we remove those silences first in an automated way by averaging the signal, getting its energy measurement and comparing against the threshold. When the threshold is too low, it probably means a silence. And we do this at the beginning and at the end of each pronunciation. This is not fully error prone, so we still verify manually that the silences have been well removed to ensure a high quality data set. Additionally, sometimes the person submit their data sample, but then it's not in the correct class, or there's a lot of noise that we cannot really know what the letter is being pronounced. So we had Arabic language experts who manually labeled and cleaned the data set and made sure that anything we're processing later is of high quality. Now, we do acknowledge something is that in its current form, 10,000 utterances over the 112 classes is still a small data set. So we are gonna be working on promoting that. So just to give you an example, against the benchmark data set, for example, the MNIST data set is a 10-digit data set of handwritten data sets. It's used to train classifiers that can recognize those digits from handwriting. And this data set has basically around 7,000 data sample per class. So we are hoping to reach such an amount for each class to have at least 7,000 and have this data set as a benchmark. So when the Arabic experts were cleaning the data, we rejected around 11% of the data due to high noise or improper pronunciation. And then also we split the data as training and test data sets. And we augmented because as we said, the data set in current form is not balanced. So we used different techniques to augment the data set. We applied randomly one of the techniques, either, for example, Gaussian white noise. We're just adding noise from a Gaussian distribution to the sample. We also applied pitch shifts randomly, whether it's up or down, and this is facilitated by ASR libraries like Librosa. We applied time stretch, make it faster or slower, and then circular time shift. We take samples from the right, we put them on the left, we make some confusion. So we we balance the data set by augmenting until we reach around 30K samples. And this is where we actually trained the classifier after. So let's see some metrics that can show the quality of this data set and how can it be used to assess the performances of state-of-the-art models. So we consider the baseline model that is available online at the Hugging Face platform. Basically, it has a base of WAF2VEC2, and then it has been fine-tuned to the Arabic language. It's the WAF2VEC2 large XLSR. So this model has been fine-tuned by Jonathan Grossman, and it's available online, open source. And we basically tested huruf, the test part, the test data set, the test group of the data set. So huruf means letter in Arabic, it's the name of the data set. And we tested the accuracy of the WAF2VEC2 Arabic on this data set, and we obtained 37%. So we also had to do this accuracy computation manually because the WAF2VEC2 would give us many classes, and so far we haven't automated this part. But we also asked the Arabic expert to be very generous while grading the model so that we get the highest possible achieving performance. So for example, if we're saying if the class is basically A, and then the model predicted A was an elongated A, we still considered that correct. So it was targeted to be very generous. And despite that, 37% of accuracy was obtained. So then we defined a very simple multi-layer perceptron, a simple neural network. And in the paper, there's the architecture of this network with 112 output classes. And we, over 9 epochs, we could see that the accuracy went to around 76% on the validation, and on the test, 65% approximately. So basically, this indicates that the classifier is learning something from this data set and is often an indication of a good quality data set. Now, if we look at the per class accuracy of the classifier, so this is, of course, as we said, it's after augmentation and balancing the data sets. we noticed that so here basically we're looking on the x-axis of the class index from 1 to 112. And on the horizontal, the vertical axis, we have the accuracy for each of this class of the base neural network. And we notice that some letters are harder than others. They have much lower performances than other letters. Some have very high performances, which shows that not all the letters in Arabic are basically equal or might need the same number of training samples, and could be an indicator which letters are harder for a classifier to accurately recognize than others that could be easier. So this could actually pinpoint where do we need to ask our users to feed more data into which class, and could be used in such a way. Now, if we compare the same accuracy of the neural network, the class 1, the classical multi-layer perceptron, with the WAF2-VEC2 XLSR that has been fine-tuned on Arabic datasets in terms of accuracy, we can see that the WAF2-VEC2, for some letters, I don't know if you can see my mouse, but for some letters, for example, it was unable to predict any of the samples. While for others, it was surpassing the base, the simple classifier. But this is a good indicator that actually the state-of-the-art model can benefit actually from such a data set that is letter level, a phoneme level. So yeah, there are letters that has really low performances, some that have higher performances. And always recalling that the data set is still small, but augmented. So these results are still kind of supportive. Now, in the second part, it's basically to talk about stability analysis and robust training. And that is an important question because we want our classifier, if we perturbate a data sample, to still, if this perturbation is a small, we don't want the classifier to completely diverge and misclassify our data sample. So it's a good assessment to test the robustness, especially in speech recognition. And then the idea is how can we make our classifier, if it's not robust, how can we make it robust? And how can we measure that? So let's start with adversarial training. And that is a known technique in AI today. It basically considers a pair of an input, basically X, Y. So X is a data sample and Y is the label. We have our model, which is mainly a neural network, F, and it gives us the output. So the output of F is basically the output of this model. It's often parameterized by theta, which are the weights of the network. And we'll also define a perturbation budget. So how much do we want to confuse our model? The higher epsilon, it means we're confusing it a lot, and that could be not realistic. So usually we choose an epsilon that is, it's a well-chosen one, such that it's a realistic amplitude of perturbation that can represent a realistic noise in real life, and so on. And the adversarial training basically is, the idea is to change the weights of the network such that we are minimizing the worst case risk of misclassifying this data sample under the perturbation. So basically we are trying to optimize this function. We have our loss function, which is basically measures the error between a perturbed data sample, so X plus some delta, and we are measuring how distant is the output of this classifier to the real label, Y. The higher L means the higher the error. So we're trying to find the maximum of L while still constrained, while delta is not anything, but still constrained by epsilon, because we're trying to find the worst case errors that we can find. And this is the risk, basically. And we're trying to train the network such that we protect against this worst case risk, and which is not, which is what the one that you want to avoid. So adversarial training, the citation is here, then tries to find the weights that could minimize this worst case risk. And this often means that If I have a very performant network, I'm actually changing the weights. So actually its accuracy is no longer the same. It changed, but it's more robust. And we'll show you some results after. And so if I adversarially trained my network, how can I now test its robustness against a certain perturbation? And how can I pick a perturbation that is relevant for me to say, oh, this is something that can happen in real life, and this is a good example to test against. So projected gradient descent is the state-of-the-art kind of method to find those good examples that exploit the vulnerabilities of a neural network. And it is known that if a network is strong against projected gradient descent perturbations, it means it's strong against a lot of gradient-based perturbations. And that's a good indicator of the robustness of the network. So how does projected gradient descent work? Basically, we'll start with an initial point around the data sample X, but still constrained by an epsilon ball around X. And then we are basically gonna update this distance delta between X and the perturbed example that we wanna find based on the sign of the gradient of the loss function. So what this means is that we're gonna go in the direction where we want to have a higher error. So what does higher error means? It means that we want to go against when the gradient is negative, and we want to go with when the gradient is positive. So we're studying the sign of this gradient, and then we are increasing the separation, x, the delta, if we are in the direction that increases the error, and if not, we are going against that direction. And then we have a projector operation because we want to keep our perturbed sample within epsilon. Because, of course, I can always choose a very high epsilon and say I confused the model, but that's not realistic. We want it to stay in an epsilon ball. So that's what the projector, the projection operation ensures, that we stay in this ball. So once this is computed, we can generate a lot of examples that can confuse the network and test the accuracy, how much of the drop it is. So let's show you some results about this. So the same MLP model is adversarially trained. We notice that the validation accuracy dropped. It is now 67% on the validation and then around 59 on the test. It is known that when we adversarially trained, the accuracy drops, but it becomes usually more robust to the perturbations. And it's not a big drop, it's around 10% for in both cases. And then this comes basically from what I said in the previous slide, is that we're changing the weights. So we're changing the weights. Of course, now we're not looking for the weights that minimizes the loss function. We're actually looking for something that still gives us good performances, but avoid us the high risk of misclassifying samples. This is some results on the MLP classifier of the roof. So let's consider in blue the non-robust model that has not been adversarially trained, and the orange models that have been adversarially trained. And then basically, what is the accuracy drop under different perturbations? So we could see for the non-robust model, the accuracy drops by half as soon as our perturbation envelope is around 0.05. It continues dropping to something. So here we're almost guessing, because 1/112 is around 0.08. So at this time, the classifier is completely useless. While the robust version still has a drop in accuracy, but still maintains somewhat a performance that is much better than the non-robust version. So some quick perspective, and then I am done. So our main perspective now is to increase the size of the data set and show if these results still are there, still showing the same thing. Maybe identify which letters are more confusing than others to ask for more samples on those specific classes. Also, we want to investigate how we can use letter level models to help with word level pronunciation, and how could these be used to improve the performances of the state-of-the-art models today, such as Whisper and Masterpack 2. Also, we want to investigate how can we use a good phonetic segmenter in order to cut a word into the phonemes and then assess each phoneme if it's pronounced correctly or not. We think this is a very good application also as a direct perspective. So thank you, and this is my talk. Please tell me if there's any questions.